mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning, physics class. Welcome to Thursday morning, May the 14th. And today we're just going to go over some of the questions that I gave you on the handout, on the Sound Waves Review handout that you got yesterday. And before that, let's get to our verse of the day, which today comes from Matthew 20, verse 28, where it says, "Just as the Son of Man did not come to be served, but to serve and to give his life as a ransom for many." It's just a reminder that just as Jesus did not come to be served, but to serve, that should be our attitude as well. Let us look to serve one another as we go through our day today. All right, going over some questions. I had a couple of questions submitted off of the assignment, so we want to just go over them a little bit, and then you're going to get another assignment at the end of this lesson out of your textbook, so you can look for that, the page number and numbers on Connect. All right, question 34, first of all. So question 34, here's my textbook. Question 34 says the following. It says that we have a stationary loudspeaker sending out waves with a frequency of 400 hertz toward a wall 10 meters away. So if I'm projecting a sound this way towards a wall 10 meters away, that's acting like a closed column. Then says an observer walks perpendicular towards the wall, so walking towards the wall, and notices a series of points where the sound is the loudest. The speed of sound is 340 meters per second. How far apart are those loudest sounds? How far apart are the maxima? So again, those maxima are going to happen at the resonances. All right, first resonance, second resonance, and so forth. And remember that resonances happen at spacing of 1/2 the wavelength. So we have to, again, find the wavelength. We're told we have a frequency of 400. We have a velocity of 340. Wavelength then is 0.85, and 1/2 of the wavelength is 0.425 meters. Now the answer in the textbook is wrong. In fact, I have a solution thing for this textbook, and in the solution thing, they have 340 divided by 400 equals 0.77. That is not correct. That is in fact a typo. It should be 0.85, which gives you 0.425 meters for the spacing between the resonances. All right, moving on to question 49. Question 49 says we have a closed tube, 30 centimeters long, shortest resonance length in a room where the air temperature is 25 degrees Celsius. So again, we have this set up here, and the question says find the wavelength and the frequency of the tuning fork. So we have a closed column, 30 centimeters, producing first resonance frequency. Again, what we have to remember is that 30 centimeters in a closed pipe, if this is the situation for the first resonance, is equal to 1/4 the wavelength. That gives us a wavelength then of 120 centimeters, or 1.2 meters. The velocity of sound at 25 degrees Celsius is 347 meters per second. Again, we have a calculation for that. Feel free to do that. Okay, and it's at 332 plus 0.6 T. I think that's the right one. But again, that one's in your formula, in your textbook, and you can find it. All right, so then we want to find the frequency. So that's A was at 120 centimeters to 1.2 meters for the wavelength of the sound. And then to find the frequency, we're going to do velocity divided by wavelength, which just found the velocity at 347 divided by the 1.2, giving us a frequency of 289 hertz. All right, let's move on to the next board, and we've got other two questions here. The other two questions I was asked was question 51 and 53. And so in question 51, we have a whistle. It's 5 centimeters long. From its opening to its closed end, important closed end, find the wavelength of the sound emitted if the speed of sound is 344 meters per second. So again, here's our closed pipe our closed system, 5 centimeter length. Again, that 5 centimeters is a quarter of the wavelength, which means the wavelength is 20 centimeters, or 0.2 meters. Frequency, velocity over wavelength, 340 divided by 0.2, 1,720 hertz, or as the textbook had it in significant digits, 1.7 times 10 to the 3 hertz. And again, I think where we're getting caught up on these questions is this first part right here in finding the wavelength, remembering that the first resonance, the loudest sound, if we don't change anything else, will happen at 1/4 of the wavelength. All right, question 53. What is the length of an open air column? Okay, open air, key. That resonates at its first resonant length with a frequency of 560 hertz, speed of sound 350. So here's our setup here again. We've got an open column now, and we want to find the length of that open column. Remembering that at the first resonance, the length will equal to 1/2 the wavelength. Okay? We're given frequency, we're given velocity, so we find the wavelength. Velocity divided by frequency, we get 0.625 meters. Going back to the beginning, we had d, the distance, the length of the pipe, is 1/2 the wavelength, so 1/2 of 0.625 is 0.31 meters. All right, so again, a few things to remember, just the properties of where the resonances happen. In a closed pipe, the first one's at 1/4 of the wavelength, in an open one, it's at 1/2 the wavelength. Resonance spacing is always 1/2 the wavelength. So there you go. All right, you can look on Connect for an assignment that is at the end of the chapter on sound, the end of chapter 15. You can look on Connect again for the page number and the numbers of the questions you are to do. Again, as always, if you have any questions, make sure you email me and we will go over them. Again, remember that there is a test coming up soon. It may be posted as early as Friday. We'll see how things go. It'll be Friday or Monday. The test will be posted. And then after sound, we're going to move on to light. See where that goes. All right, that's it for today. Have a great day. See you tomorrow.